Okay, let's continue with lecture 1D. In the last lecture, we have discussed the general equation to determine stresses on inclined planes. Okay, with a simplified equation. Now let's see how it's being used in this example. In this example, we are given a stress element, right? And the stress element is in the orientation of the x and y direction. So we have x over here, that is x direction, and here we have y direction, okay, up here. So we have the original orientation in the primary direction, okay. Here if we take a look, it says find the stresses or state of stress at this same point when we orientate this element 30 degrees clockwise. So what it wants us is to rotate the stress element 30 degrees. So the final direction will be x prime, which is 30 degrees to the original direction. Okay. So in the equation, we have a simplified equation where we have sigma x plus sigma y over 2 and so on. Now, sigma x in this case is 80 megapascal. So that is sigma x. So it is 80 megapascal, but it is compressive. So it is negative. So sigma x, we have here sigma x is minus 80 megapascal, right? Sigma y here is tensile, so it's positive. So we have sigma y is positive 50 megapascal. Okay. Tau xy. Now, tau xy is referred to the right hand phase. So in this condition, it is in the x direction phase. So it refers to this tau xy here, right? This tau xy is downwards on the right hand phase. So when it's downwards, it is negative. So we have tau xy is equal to minus 25 megapascal, right? So those are the basic values that we need to use in our solution. Okay, and our angle. So if we want to find the x prime direction, the angle here is clockwise, therefore it is negative. Okay, so theta x prime is minus 30 degrees. So if you want to find the other direction, that's y prime, then it is positive 60, right? Is the other direction here. Okay, so we have y prime, that is y prime direction, and the angle to y prime is that angle there, and it is 60 degrees. So theta y prime is 60 degrees. Or if you don't want to call it y prime, can call it x2 prime. It's the same thing. Now, the textbook, if you use the textbook, then it will also give you the solution, right? So we have sigma x is minus 80, sigma y is 50, tau xy is minus 25. Our general equation, the simplified general equation that we have is this equation here. Sigma x prime is equal to sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 cos 2 theta plus tau xy sine 2 theta. So what we then do, this equation we have to memorize, and then we just put in the values. Sigma x is minus 80, so we have minus 80 here. Okay, so it's minus 80 plus 50, sigma y is positive 50. Then we have sigma x minus sigma y, so minus 80 minus 50 over 2 cos 2 theta. And theta here is clockwise, remember? So it's minus because it is clockwise. We put cos to negative 30. And then tau xy is negative, so plus tau xy. So minus 25 is tau xy. And again, theta is minus 30. So if you calculate this, you will get minus 25.8. So remember, it's a negative value. What it says here from the answer is sigma x prime is compressive. So if you want to draw, so you have to draw it in a compressive direction. So we have, that is sigma x prime. And so you just put the value there as 25.8 megapascal because you already have put the direction as compressive. Do not put minus there because the direction is already the right direction. You only put a negative if you put a tensile direction. Okay. And for tau x prime y prime, we use the second simplified equation here, which is equal to minus, don't forget the negative there, minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cos 2 theta. It's still the second part of the equation, but slightly different because it starts with a negative. Okay? And cos becomes sine, and sine becomes cos. So we just replace all the values in this equation. So we have this second equation here. And if we calculate, we get the final answer here, which is a negative. So we know that tau x prime y prime on this surface here, the right hand surface facing x prime, is negative. In other words, it is facing or moving downwards. Okay, so tau x prime y prime is downwards, and the value is 68.8. So we just put a value there, 68.8 megapascal, and there is tau x prime y prime. And for the other surface here, BC, okay, you can call it y prime, or you can change the direction and call that now as x prime, as shown in the text. Or you want to call it differently, you can call whatever you want, x2 prime, or whatever reference you think will make it easier for you to understand. Okay, now again, we can use the same equation. Remember, this is the same equation. Sigma x prime is sigma x plus sigma y over 2 and blah 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 until the end. Okay, so we replace. Now the angle is different. Remember, this is the angle now for this plane here. Theta is positive 60. The only difference between this and the previous answer we calculated was theta. That is the only difference. Theta now is positive 60 instead of minus 30. So if you evaluate the same equation with a different theta, now we get minus 4.15 megapascal. Is compressive minus? So we put a compressive stress here. So it's compressive. And the value now is 4.15. You don't need to put the negative sign, right? Now, you do not need to do this. You do not need to do this if you don't want to. This, you don't need to do if you don't want. But this answer is shown here just for checking, to make sure that your calculation is right. The previous calculation and this calculation will confirm the answer is 68.8 megapascal and the direction, right? Remember, the earlier calculation gives you this one. It's negative, so it's downwards on the right hand face. Now this calculation confirms the answer. Now you get positive, meaning on that right hand face there, it is upwards. Okay, this shows it upwards on the face that we are considering. That is the right hand face. Okay, it is moving upwards, and the value is still the same, 68.8 megapascal. So it's just a checking calculation. But if you do not do that, it's fine, as long as your answer previously is right. So that final stress element that the answer wants is this figure D here. So that is the answer with all the stress acting on the four surfaces shown with the correct direction and the correct values. So we have seen basic equations. First, we have this basic equation here derived from the triangular element, okay, equilibrium of forces from the triangles. Then we simplify those two equations to get this simplified basic equation. Now these equations, these two will give you the normal and shear stresses at any plane with angle theta, right? So you can determine at any plane. So the question now comes is, what's the maximum stress values and which is the direction of the plane, which will give you the maximum stress value. So to answer these two questions, now this is what we do next. Okay, we want to find the maximum stress values and we want to know direction of the plane where it occurs. So for that, we will do what we call determination of principal stresses and maximum shear stress, right? And to get those equations, what we do is from the basic equation, these are the basic equation. We have 2, we also have sigma y prime if you want to, but you don't need to memorize this equation here. You just change the angle theta and you will get sigma y prime. Just add or minus 90 degrees to the basic angle, okay? Because they are different by 90 degrees. So from this basic equation, remember mathematics, finding maxima and minima, we just differentiate the equations. So we differentiate sigma x prime with respect to theta. We can also differentiate tau x prime y prime with respect to theta, and we will find the maximum and minimum values, right? So if you do that, then you will get a final equation, not exactly that. Now we get this equation here. If we differentiate the equation and solve it, those two equations, we will get this equation here. Sigma maximum or minimum is equal to sigma x plus sigma y over 2 plus minus square root of sigma x minus sigma y over 2 square plus tau xy square. Now that is called the principal stress equation. And what is the principal stresses? It is sigma max and sigma min. You have two values. You have a maxima and minima when you draw a curve, right? So we will get it from this equation here. And this equation here, tangent to theta p, will give you direction of the principal plane. So it's called the principal planes equation. We give you two values of angles to give you direction of P1 and P2. So you have two principal planes. One is facing X prime and the other is Y prime, which will give you the largest value of normal stresses. So this equation, tangent to theta P, will give you two angles separated by 180 degrees because it's 2 theta P, or you can then divide by 2 and you have two angles separated by 90 degrees. Similarly, for maximum shear stress, you will get this equation here. Tau max is equal to square root of sigma x minus sigma y over 2 square plus tau xy square. Now, if you notice, this equation is equal to the second part of the maximum normal stress or principal stress equation. Okay, it's the second part of the equation, the square root part. And the plane is given by this equation here, tangent to theta s which stands for shear, is equal to this equation here. Now, you might want to remember this equation, but you do not need to, actually. You just need to remember the first equation, tangent to theta p. Okay? So you just need to remember the first equation. So this diagram at the bottom here, this diagram here gives you the stress element, how it should look like when you have tau max. So tau max is the maximum shear stress, but on the plane itself, you also have normal stress. Now, if you notice, the normal stress will be the same on all the planes. Whether it's sigma x prime or sigma y prime, it will have the same value. Now, this stress value here is called the average normal stress. Okay, average normal, that's M there, stress, average normal. Okay, when you have maximum shear stress, you have average normal stress. When you have maximum normal stress or principal stresses, you do not have any shear stress on the plane, right? That's the average normal stress. And if you remember, this is actually the first part of the principal stress equation. Because the principal stress, sigma max, sigma min, sigma 1 or 2, sometimes written, is equal to sigma x plus sigma y over 2. So that's sigma average. Plus minus, right? Because square root have two values. Plus minus the square root of whatever you have up there. Sigma x minus sigma y over 2 square plus tau xy square. So you have a square root of this, which is equal to r, right? So it's equal to r. So it's equal to sigma average plus or minus the radius, r. Okay. Now, r here is radius of a circle. So in other words, is tau max. We'll talk about r later. But this is the principal stress equation. And from this principal stress equation, you also get the solution for maximum shear stress from the square root and the average normal stress in the first part. Let's see how it's used. Okay, we have this example here. Now in this example, we have a stress element again in the primary direction. This is x, this is y. Okay, those are the primary directions. So we have sigma x, sigma y, tau xy. So in this problem here, we have sigma x is positive 50 megapascal. We have sigma y is negative 10 megapascal, is compressive, right? And tau xy here on the right face, because our main reference is x. On x here, it is upward, so it's positive. So it's positive 40 megapascal, right? So it says here, for the state of plane stress, determine the principal plane. First, he wants to know direction of the principal plane. Or which direction do you get the maximum normal stress or principal stress? Then what is the value of the principal stress? And then the maximum shearing stress and the corresponding normal stress. This is sigma average. Okay, normal stress. So the solution step given in the textbook, first it says find the plane. That's the solution for question A. Okay, principal planes. So the equation is 2 tau xy over sigma x minus sigma y. This you have to remember. So that's the first equation that you need to know. This equation gives you direction of the principal planes. Next, you determine the principal stresses from the principal stress equation. Then you can calculate the maximum shearing stress, okay, and the average normal stress. So if you look carefully, this equation is actually the second part of the principal stress equation. And this here is the first part of the principal stress equation. So if you remember just the principal stress equation, you can answer both of them. So there's only two equations you need to memorize. This equation here, right? And this equation here. Only two equations, if you really understand what they are. So the first part, tangent to theta is 2 tau xy over sigma x minus sigma y. Put in tau xy is positive 40, sigma x is 50, and sigma y is negative 10. So you have sigma y there. And you get 1.333. And remember, this is in radian if you change the angle. Okay, you change the angle, tangent to theta p, you can get in radian or you can get in degrees depending on your calculator setting. So it's giving you radian or degrees. From tangent to theta p will give you the answer will be either radian or degrees. Right. So if you calculate 2 theta p is inverse tangent of 1.333, you will get two values. One is 53.1, the other is 180 degrees away, because it's 2 theta p, 2 times the angle. So if one, just theta p, you see the difference here is 90 degrees difference, right? Plus 90 degrees. So you get two angles. Okay. Then use the equation for principal stresses. There is theta. So if you draw, first theta is positive 26.6. So from x going to x prime, this direction here. So theta p is 26.6 positive counterclockwise. The second angle 116 will give you this direction here, y prime, okay, plus 90 degrees. The values, sigma x plus sigma y over 2, sigma x is 50, sigma y is minus 10. So you have 50 minus 10 is 40 divided by 2 will give you 20. Right? Then sigma x minus sigma y, 50 minus negative 10 will give you 60. Over 2 will be 30. Right? So you have 30 square. And tau xy is positive. So it's positive 40 square. If you solve the problem, you get the maximum value is 70 and the minimum value is minus 30. So on the x direction, it assumes, but you should not do that actually. Okay. However, the answer here is given as sigma max is on x. Sigma max is on the x-axis, 70 megapascal, positive, so it's tensile. And sigma y is minus 30, so it is compressive. Now, caution here, I would like to take, do not always assume like this, because sometimes the maximum value is not on x prime. The minimum value is on x prime, sometimes. And I assure you that sometimes in your test or exam, we purposely make sure that that is the case. So if you just assume this, you get your answer wrong. Alright? So what you need to do is this. Now remember, you have this angle here. and you have these two answers. Okay, so what you need to do is you want to check which principal stress is on x prime, which one. So what you do, you use the basic equation. Remember the basic equation? Sigma x prime is equal to sigma x minus plus sigma y over 2 plus sigma x minus sigma y over 2 cos 2 theta plus tau xy sine 2 theta. Right? You have that basic equation. What do? You take this angle here. For example, you take 26.6 degrees. That's the first angle here, right? That goes to x prime. That is 26.6. Put in this equation. Okay, theta, put here. And here. Put in all the values of sigma x, sigma y, and tau xy. And calculate for sigma x prime. So when you put 26.6 here, you will find sigma x prime and check which of the two is this value here. With this equation, you are confirmed not to have any mistake that one of these will be on x prime, because you have checked. This is for checking. Okay, you check to make sure that it is correct. So if you put this value, for example, you put these answers here, right? Sigma x, sigma y, tau xy, and the angle 26.6 times 2, you will get 70 megapascal. So this assumption is right. But in certain cases, it goes to the minimum value instead. So you have to check. Okay? And maximum shear stress, remember, is just the second part of the equation. That part there, the square root. Actually, you don't need to do separate calculation. You just point out that is the equation. The value comes from your earlier calculation. You already have this value here. It's 50 megapascal. It's positive. Therefore, on the angle, on the direction, you get this. But again, you need to know whether is which plane is having positive and which plane is negative. They are all the same, right? 50 megapascal, but they have different direction, positive and negative. Again, you have two angles. You can use the equation given earlier, or you just use this simple relationship. We know that the maximum shear stress plane is always 45 degrees apart from the principal plane. That's the principal plane angle. Remember, you have 26.6 for the first angle and 116.6 for the second angle, right? So if you minus or you add 45 degrees, you'll get the the maximum shear stress plane. In this case, you take 26.6 minus 45, you'll get that angle. If you add 45, you'll get this angle, right? So that's how you solve for maximum shear stress plane. But then again, remember, you don't know which plane will give you a positive and which plane will give you a negative answer. So remember, you have your tau x prime y prime equation, right? It's equal to minus sigma x minus sigma y over 2 sine 2 theta plus tau xy cos 2 theta. You have the equation there. Use the equation. Replace theta with the first one. Probably you replace theta with 18.4. So what you then have, you have the final answer. Okay. 18.4. So you have 18.4 is negative. So you are pointing to that direction there, right? X prime. and you will find that tau x prime y prime will be positive, meaning it is going upwards on that phase. Okay? If you replace 71.6, you'll get a negative value, so that negative value will give you a downwards force on the right hand plane, because you are talking about that axis now. Okay, so that is y prime axis. And on all the planes, when you have the maximum shear stress in plane, you will also have the average normal stress. Okay, and the average normal stress is the first part of the principal stress equation. Again, you do not need to do any calculation twice, just use the answer. And so that answer is 20 megapascal. So it's shown here, all of them are 20 megapascal on both the directions x prime and y prime. So you have all four of them 20 megapascal.